All right. Let's get started. Yeah. So yeah, welcome to Wednesday lecture. So we're going to jump into chapter 9 today, and cover a lot of the material there. Before we do so, I do want to quick just chat. So remember, so you have your assignment 9, or your Connect assignment on chapter 9 due this this Sunday. But you also have the exam coming up. So midterm 2 is scheduled for to be due at some point this Tuesday. It'll follow the same flow, same format as the first midterm, and so you'll have kind of an extended period to work on it, and that'll be sometime. You can expect to have it available on Sunday, and then have all day Monday to work on it, and then I'm going to have the due time be noon on Tuesday, and so that'll be a little different. I think the first midterm you had later in the day, but I don't want you to have to make decisions about, do you spend time working on the exam or do you go vote? So this will kind of force you to be done with the exam by noon, and obviously, again, most of you turned it in, the day before anyway for the first midterm. So, on Monday, you'll have all day Monday and some of Sunday to work on it. So hopefully it won't be put to the end, but if it is, that way you'll be forced to turn it in, and you can still go get in line if you haven't made a plan to vote, or if you haven't, voted early or whatnot. Yeah. So, and we'll have more to talk about election stuff later today, because we can look at some polling for what we're talking about in chapter 9. So to set that up, and maybe just to refresh your memory, so for the exam, you can really think of it as covering mostly chapters 5 through 8. Sorry, 5 through 9. 5 through 9. Your voice keeps. Oh, I will see if I can. Oh, you know what it is? Let's double check. Okay, that's. Oh. Microphone. Let's have the mic come from right next to my mouth instead of across the room on the camera. So hopefully that helps. Thanks for pointing that out. Okay. So yeah. So the exam, you can think of chapters basically 5 through 9. I know chapter 5 was covered in the previous midterm, and I won't spend a lot of time on that on the midterm. But obviously chapter 5 dovetails quite nicely with what we're doing now. So in chapter 5 was probability concepts, and from the from counting, so combination formulas, that's where we first came across that, understanding what a likelihood means and summing all of the possible outcomes and multiplying and those types of things. So we'll focus more on 6 through 9, but obviously chapter 5 plays a role in that. In chapters 6 and 7, we largely learned about discrete and continuous probability distributions. And this was within the population, so we would we learned about weird looking distributions. We spent a lot of time on normal distributions, uniform distributions. We did discrete, right? So these types of, whether it was the free throw example or whatnot, different types of distributions. That's what we're learning in chapter 6 and 7, how to handle those, how to calculate areas underneath the curves. And in chapter 8, what was the big takeaway from chapter 8? Was based around the central limit theorem. Okay, and the concept was all of these, if we're sampling, samples become If it's a random sample, we get to the normal distribution. Okay, so in Chapter 8, we learned how we can handle all of these. If we are sampling, it fits into a normal distribution, and that led us down some useful routes. But we had spent a lot of time in the theoretical world, right? So we were thinking about taking 255 billion different samples and what would it look like and all of that. Okay, so that's kind of where we are. In Chapter 9, we now enter reality. Okay, we're gonna do things that we would actually do to solve some real questions. Okay, so all of this was necessary. We have to understand the basis of it, but of course, we never take that many samples. What do? We take a sample or something like that. Okay, and so what's true about Chapter 9, or why it's so well? Actually, let me just write this down for just reference. Right, we built we built this in Chapter 8. We built the normal distribution and the z-score back in Chapter 7. Okay, what are we doing in Chapter 9? Well, we are being honest with ourselves and saying we don't actually know some of this stuff. Okay, we're going into a world, or we're curious about something out in the world. We say, hey, I'd like to know the average income of this group of people. That's why I'm going to take the sample. Okay, so oftentimes we take samples because we'd like to know something. We'd like to know what the population mean is, but we don't know. Okay, this is our question that we're after. And so our methods thus far have relied upon knowing that, which again is not practically often the case. There are cases where this is true, where you do know it, but oftentimes when we sample, we don't know it, and we also often don't know the population standard deviation. And so that's where we are in chapter 9, is dealing with how do we deal with this? How do we use sampling to give us a good guess as to what these might be? Okay. So that's kind of a blueprint of where we are. So today we're going to deal with how do we manage situations when we don't know these. We're going to first start with the idea that we're going to set this aside for now. So our first run through it is going to say, okay, let's actually say we do know the population standard deviation. Okay, and once we've built the structure of how to handle this, we will then come back and say, all right, we now don't know this. And it'll change a couple things, but the flow will be the same. So in our first example here, we're going to talk about knowing the standard deviation, but we don't know the population mean. Okay, so just for sake of an example, we're going to say we're curious about the what's the average height on campus, or of all students. And so we don't know it. So what could we do? We're going to take a sample, and we're going to say, let's say we decide we're going to do a sample of n equals 25. Okay, we're choosing this, and I'm making it up, but let's say we're going to sample 25 students, and we come out. What are we going to get from a sample? We always get an x bar, right? We can calculate the average of the sample. Let's say it comes out as 64 inches. Okay, so we don't know what. Remember, we don't know what the population mean is, but we're trying to find it. We're trying to get a feel for what it might be by taking this sample. That's the point of the sample. Okay, so what is our best guess going to be? We're going to take a good educated guess, our estimation of the sample mean. What we're going to rely upon is, well, if we've taken a good random sample, right? We've done the sampling well. Then we can kind of make this statement that the sample mean is probably close to the population mean, right? That's why we're taking the sample, is because we think we can get a feel for what the population mean might be. So we're relying upon this idea. I'm kind of using the fuzzy, roughly equal to. For math majors, I'm sure there's more nuance to that, but this is what we're relying upon. This is basically the population mean. Now, it's not the population mean, okay? So there's an important caveat there. We think it's close, but we know it's not the true mean. We just don't know where the true mean is, or the population mean is. But when we say, give us your best guess, if we know nothing else about the situation, we might as well guess that we think the mean is 64. Okay, because our sample was 64, our sample mean was 64, why not guess 64? Now, rewinding. In Chapter 8, when we took a sample, we always put it back on the sampling distribution. Okay, where we knew, just for sake of argument, I'm going to talk about different numbers so we don't get too confused. But let's say we were dealing with something and we knew the mean was 12, the population mean was 12, and we got a sample mean of 15. And then we'd have a discussion about, okay, how likely would it be that you got somewhere between 12 and 15, or maybe above 15, and we could calculate that percentage. We don't have that over here, because remember, this relies upon us knowing, well, yeah, the mean is the population mean is 12, so the mean of the sample means is 12. We had all of this information, which all relied upon knowing the population mean. We don't know that over here. And so all we've gotten thus far is a value of 64 for our x bar. But what we don't know is where this distribution falls. Okay, so it could be that we got a value that's below the mean. Maybe the mean is up here. Maybe it's 67. Okay, that's a possibility. This same sample, though, could have been maybe the true mean. I'll switch colors here. Maybe the true mean is actually down here. Okay, maybe it's 63, and we happen to get 64. Maybe it's really close. Maybe we almost hit it right, and it's 64.02. The problem that we have here is that we don't know which of these distributions we're on. All we know is that we got 64 from this sample. So we don't know if that sample is above or below the true population mean. So we know that this is probably not exactly right. And so what we want to do, and much of what we're going to do in Chapter 9 is talk about this uncertainty. We don't know exactly where the true population mean is. So the first part, I think the chapter is named Estimation and Confidence Interval. We've already done the estimation. That's simple. What's your sample mean? That's our guess. The tricky part is, how do we build this uncertainty? How do we talk about the uncertainty? How do we put numerical measures to the uncertainty? And to do that, we're going to rely upon the same thing we've been dealing with all along. The z value, or the z system. Okay, so the z calculation, I'm going to write it in this form. Okay, we know we can kind of play around with the bottom, and I'm actually going to kind of mix. I'm going to use mu here just because we're going to be talking about mu. But we know in our distributions that mu of x bar is equal to mu, right? This is true. So I'm just kind of, I'm using this form, but I'm putting in mu, okay? Because I want to highlight this top part. Okay, and the way I'm going to do that is I'm going to multiply by sigma over square root of n, and what we're left with is z times sigma divided by the square root of n is equal to x bar minus mu. So now we have this x bar minus mu kind of isolated. What is x bar minus mu? This is the sampling error. Right, we came across that a few chapters ago. The sampling error, how far did we miss with our sample mean? Again, we're always kind of assuming that our sample mean doesn't spit out the exact population mean, right? And even back when we're in this world, we know that we're often going to be off. We don't know how far off we are. Here we actually do. But in this case, we don't actually know how far off we are because we don't know what mu is. Okay, but we know that there's a sampling error. Again, possibly maybe we hit it right and the actual mean is 64. But in that case, there's still a sampling error. It's just 0. Okay, so how big is this sampling error? Again, we don't know, but we can measure it, or we can get a feel for how big it's going to be. Or I should say we can get kind of a range as where it might fall. Okay, so this sampling error, this kind of gives us a range in which that sampling error might fall. So this is actually how we're going to build our confidence interval. We're going to say, you know, our best guess is 64, but let's build in some uncertainty. So our confidence interval, or the way we're going to describe it, is to say our best guess is x bar plus or minus, taken directly from here, z sigma over square root of n. Okay, this is what we're going to build in chapter 9. Now we're going to adjust it a little bit in the latter half of chapter 9 when we don't know sigma, but it's going to flow from the same concept. So let's do that for this exact example. So 64 plus or minus. So really what we're saying is we're kind of building a window here. 64 is the middle of it, and let's talk below and above it. Now, I didn't write this down, but let's say, okay, so we said we know sigma, right? So sigma is equal to, I'm going to say sigma is equal to 4. Again, I'm making that up, but we would know that, right? In this scenario, we know the population standard deviation. Again, not really common that we would, and so we'll have to make an adjustment for that. But for here, if we do know it, let me plug that in. 4 square root of n is square root of 25, right? We took a sample size of 25. And z, what is z? Well, z is our z table. It's our z table z, right? So we have been making this transformation between z and some percentage that we're interested in. We've been doing that for a few chapters now, right? And we look up the value. We can go both directions. We know we can go from z to a percent and from a percent to z as long as we're reading the table in the right way. So confidence intervals, this is where we have to make a choice. We have to kind of give a level of confidence that we want to be able to discuss this in. And so you can make any percent confidence interval you want. Typically, we see 90%, 95, and 99 are the most common. But you could have an 87%. You could have 99.99%. You could have a 12%. I don't know. But most common are these three, and within it, 95 is probably the most common. It somewhat depends on kind of the conventional norms within the field that you're talking about. So if you're doing presidential polling, they may have a certain confidence interval that they often use. If you're doing estimates of income, there may be a slightly different one. But we, as if you're the data analyst, it's up to you to kind of make that decision. Again, referencing kind of the social norms or the conventional choices. So let's use the 95%. How do we find the 95% confidence interval? Well, in the Z table, so the confidence interval is plus and minus, right? So we're talking two directions. And so when we think about the Z distribution, we're really going to have both sides active. Okay, so this, to get 95%, we really look for 47.5 and 47.5. And that combined is going to be 95%. of the window. So when we turn to the z-table, we look up 0.475. It gives us a z-value, right? So we're looking in the table, finding 0.475, and then we're going out to the z-value, right? This is that kind of the reverse of the initial way where we look up the z-value, found the percent. Here we're finding the percent, finding the z-value associated with it. So that's going to give us 95%. Again, if you're looking for 90%, it would be a slightly different number. When you look that up on the z-table, and we can do more of this on Friday when I can pull it up on the screen, but you're going to find a very familiar number, at least by now. Right? You've been forced to look up 95% or 0.475 a few times in the homework, I'm sure, and that gives us 1.96. Right? That's the value up at the top of the z-table in the little shaded range, because 1.96 is such a common number, because it is that 95%. It's close to that empirical rule, right? What's the kind of empirical rule tells us? 2 standard deviations, 95%. This is that more specific, the exact value. Empirical rule is just a rounding of this. So we're going to use 1.96 for our z-value, right? We wanted 95%, and that gave us 1.96. The 1.96 gets plugged in here, and that's all we need for our confidence interval. Let's see if I wrote down some. So this is 4/5, so it becomes 1.57, roughly. Okay, and so this is our confidence interval, or that's one of the ways to describe it. You'll sometimes see it written like this. So this would be 62.43 so I've done the minus. Now let's do the plus. That'd be 65.57. Right, so all I've done here is kind of make the range. Usually do a little bracket around it. And so both of these are acceptable ways to describe this confidence interval. Okay, but now what we've done here is we've shown our uncertainty. Okay, so rather than just say our sample of 25 students showed 64 as the mean height, so that's what it is. We don't know for sure that's what it is, and so we're giving some level of uncertainty. We think it's, roughly speaking, we think it's near this range. Okay. Now, the exact nature of a confidence interval is there's kind of a nuance to it. I have a video up that walks through the specifics of that. Yeah. So just to kind of begin that conversation, again, check out the video and read the book for the specifics of this. But so then the confidence interval, if you loosely understand it to say, this is a 95% confidence interval. So what I'm about to say is wrong, but it's close. Okay, so it's not wildly wrong. It's just slightly wrong. If you were to say we are 95% sure that the population mean falls within this window, you're close. And that's not a bad way to start your understanding of the confidence interval. But I do want to highlight that that's technically not quite right. So the confidence interval, roughly, you could think of it as, let's say we go back to the theoretical world where we take a bunch of samples. Okay, we could take another sample here. Maybe this sample we got 65.7. Okay, we build a confidence interval around that sample, if that was the sample that we took. Interestingly, if we were to do that, nothing in this part changes, right? 95% confidence interval, 1.96 for the z. Population standard deviation doesn't change. We still took a sample size of 25. So actually, this 1.57 wouldn't change. All that would change would be our best guess. So we would say 65.7 plus or minus 1.57. Okay, that would have been the window had we taken that sample. Again, the sample is kind of random, right? So the sample is those random 25 that we selected. So if we were to do that many, many times, we think, or what the 95% confidence interval says is, 95% of these different intervals would contain the true population mean. And so in practice, those two concepts, whether you say, 95% certain that it's within this range, or 95% of the ranges would contain the true population, you're not wildly wrong on that. But as you dig deeper into statistics, the confidence interval truly means if we did it many times, 95% of them would find it. So, yeah, look for the video. I walk through kind of more of this type of a thinking. Yeah. So I want to take a moment here. So next we're gonna talk about forgetting this. Okay, but first I want to highlight that so far we have been assuming that we've done the sampling well. Okay, we've done a nice random sample or some type of sampling that adequately gives a good representative sample of our population, right? We want our sample to look like our population, or to mimic our population, in the sense that if we don't have it, this whole system breaks down. This relies upon good sampling techniques. And as we talked about in whatever chapter that was, chapter 7, we're going to spend a lot of time just assuming that we've done it right. But I do want to highlight, so for instance, we're finding, we took a sample and it showed 64 inches. That's, I made up these numbers, but that's what, 5'4", which could be. But here, as a way to kind of show where this might break down, let's say you said, I got a sample that heights of 25 students, and so I'm just going to go out and find the first 25 people I find walking around campus. I'm going to measure their heights. That might work, but what if, for instance, the diving team just gets done with practice? I don't know if I'm assuming divers might be short. They were when I was in undergrad. I don't know if that's true, but let's say they are. Let's say divers tend to be short. And you go out and you sample the first 25 people, and a bunch of them happen to be coming out, or happen to be students that have come out from the diving pool. You're going to get a sample that doesn't look like the general population. Okay, and so if that's the case, we can't trust this to be our best guess for the population mean. So that's always a caveat. That's always something that we should be mindful of when we look into studies that do sampling. How did they do their sampling? Can we trust that they did a good job of making an unbiased sample? So all of the rest of this is pointless if we don't have good sampling. Okay, so what happens? What happens when we don't know? When we don't know this information? And again, this is the most common situation, because if you don't know the population mean, why would you know the standard deviation? That's it'd be hard to find reasons for that. So let's walk through what changes. Okay, so where do we run into problems when we don't know the standard deviation? Well, our process here, obviously we're going to have an issue here, right? Because in our confidence interval, standard deviation shows up. So if we don't know this, how are we going to build this confidence interval? So that's going to be the big thing that changes. Well, it's one of the two big things. So that's where the problem lies. So we're going to change that, and to deal with that, we're going to end up changing z. Okay, so those two things need to change. So when we take a sample, so first we're going to deal with sigma. How do we deal with not knowing sigma? Well, when we take a sample, we got an x bar, but we could also calculate an s. Okay, recall it's been a month or so, maybe longer, since you had to deal with s. If you remember what s is, it's the sample standard deviation. Okay, we made a big deal about that way back when we calculated standard deviation. Are we crunching the population or the sample standard deviation? And remember, this is the one that does divided by n minus 1 instead of n. So we can always calculate that from our sample, just like we did with calculating the mean. Then we look at these 25 values and we crunch an S. Okay, maybe we get 3.5, maybe we get 4. Let's trying to think of which is. Let's say that we did. Let's say it was in fact 4. Okay, we crunched it and it also spit out 4. I think this will give us a better way to highlight the difference. So let's say we actually ended up having the right S, but we don't know that for sure, right? So remember, we don't know what the population standard deviation is. We think that this is a good guess. And in fact, that's what we're going to use to build this confidence interval. We're going to use S, we're going to rely upon, much like we relied upon X bar is roughly, it's a good guess. It's an unbiased estimator for mu. Similarly, we're going to say, hey, you know what? S is probably pretty good at guessing where sigma is. And in fact, it's also an unbiased estimator. It does a good job. But, so we can plug in S for sigma, but this brings in uncertainty. Much like we had uncertainty here, we have uncertainty here. So when we had uncertainty about where the population mean is, we said this is our good guess, but let me build a confidence interval. Okay, we don't know population sigma. This is a good guess, but let me build in some uncertainty. And this time, instead of building a confidence interval, we're going to switch from the z to the t distribution. Okay, so we just did this. Okay, and this time we're gonna say we can still use X bar, but this time we're plugging in S, still square root of n, and to deal with that we're gonna use the t distribution. And so that's how we're going to build in that extra uncertainty. So, okay, so let's play around with this and actually build this for this scenario. Okay, so we would still, let's say we took the sample and it showed 64. We do plus or minus. We're going to use S is 4. Okay, we still have square root of 25. Okay, and we could have, like, if we take a different sample, we're going to get a different S. So that S is going to change between samples. But let's say it was 4 here. Now, we need to plug in a T. How do we find T? T is very closely related to Z. And the process is the same. So just like we were able to transform between Z and a percentage, we are able to go T to a percentage. We can do T to a percentage. We can make that transformation. It's on a different table. Okay, it's kind of like the Z table. It's just structured a little different. The same concept. If we have a percent, we can find a T. If we have a T, we can find a percent. One little caveat, or one difference, is that sample size interacts here. Okay, so it's more complicated. There's a different T distribution for every n. So really the T distribution is a T distributions. It's a family of distributions, all slightly different depending on the sample size. So let's talk a little bit about that. The T, so the Z distribution looks something like this, right? It's a normal distribution. We know some of its properties. The T distribution depends on the sample size. Okay, so we can have fat distributions. I'm on the screen, I think. Okay, so this might be n equals 5. Okay, so when you have a small sample size, it's fatter. as the sample size increases, you get a little bit skinnier and a little bit tighter of a distribution. This might be n equals, 14. Okay? Now, why does it start to get tighter? Well, the whole point of this t-distribution was to build in uncertainty, right? We don't know this. We don't know the population's standard deviation. So we're building in uncertainty. We get more and more certain the larger the n is. Just like with our guess for mu, right? As the sample size gets bigger, the confidence interval gets smaller, right? So if we would have instead had a sample of 100, we would divide by square root of 100, we would divide by 10, so we get a tighter window. Right? This confidence interval will get tighter with a larger sample size. Same concept. As we get as n gets bigger, we get a little more sure about that sigma, or where we think sigma might be. Okay, so roughly equivalent ideas here. As n gets bigger, the distribution gets tighter. We have to build in less uncertainty. And it keeps going. It keeps getting tighter and tighter. Okay, that's a terribly drawn one, but n equals 30. Okay, it gets tighter to the point where eventually it becomes very similar to the z distribution. So by the time, if this is the z, by the time you have n equals, actually want that fatter. By the time you're up n equals 200 or 300 or 400, they're very similar. And in fact, at the bottom of the t-table, which we'll look at more on Friday, the last row, it says infinity, and it just gives you the values that would pop up in the z-table. So when you look at the z-table and you find 95%, you get 1.96. You'll get that if you have a very large sample size with the t-distribution. Okay, that'll hopefully make more sense on Friday. So that's setting up why we have to get the n. And so let's do that in this case. So we have n equals 25. And so when we look that up on the t-table, again, you can look at the videos, or on Friday we'll do this. You get a value of 2.064. That's the 95% t when n is 25. There's a little conversion, again, just to highlight this. You have to make a little adjustment when you go to the table. We actually look at degrees of freedom, and so this is degrees of freedom equals 24. But we won't get into that today. But you get this value when you go through this process. So it's very similar to the z. But what do we see? There's a little bit more uncertainty. This is going to cause our confidence interval to be slightly wider. Right? This is not 1.96. It's a little over 2. And so when we finally build the confidence interval, let's take this down here, we get 64 plus or minus 2.064, 4 over 5. And I don't have this crunched, but let me do that quick because we can see that the window is a little bit bigger. We get there quicker if I knew how to use my phone. So we're going to get, rather than plus or minus 1.57, we get 64 plus or minus 1.65, roughly. Okay, so what's happened here? We didn't know what the population standard deviation was, so we had to estimate it. And when we're doing that, we build in a little bit more uncertainty, and so our confidence interval is slightly larger. Okay, that's the big change between knowing the standard deviation and not knowing it. Now, this is not always going to be, so I said S happened to be 4, which was the same. So it's quite possible that we get, 3.7 and we have to plug that in. So other things can change. Okay, but what I wanted to highlight is that if we had S be the same as sigma, we still get a slightly larger standard deviation. Okay, so the two big things that we have to change are sigma, flopping an S for that, and then moving to the T family instead of the Z distribution. And again, this is, in practice, this is what's often done because this is most common, that we don't know this. And in fact, we're gonna hang out with the T distributions for the next few chapters because a lot of what we do is gonna say, okay, often we don't know this. So we're gonna use it when we turn to running kind of testing hypothesis, and we use it into regression and all kinds of different stuff because oftentimes we don't know that population. So you'll get more and more practice with the T-table as we go. And it is a little confusing, so if you open it up and you're confused, definitely reference the book or the videos to get you up and going. Okay, so I want to turn to one other concept that comes up in Chapter 9, and specifically because it is incredibly timely, given that we are now 6 days from not only a presidential election, but all kinds of elections. And so we're going to see that this same concept, this whole building of a best guess and a confidence interval, holds true for proportions, and namely polling. So we can use this for like presidential polling. And in fact, this is what pollsters do. So we're going to see, yeah, let me just, 1.7. Okay, we'll just get rid of most of this. We can write it back up if we need it. Okay, so let's say we're interested in who we think the state of Minnesota is going to vote for. Now, we need to, on Tuesday, or we'll finish kind of asking everybody. So we will, in this case, we will actually know, well, maybe not on Tuesday, but by Wednesday or Thursday, once everything's counted, we'll know actually the true value. But that's not that helpful. We want to know beforehand, okay? So what we're interested in is, this time we're not interested in mu. We call this pi, right? So pi being the proportion that's going to do something, right? Or the outcome that falls that way, right? Yeah. So we don't know pi, but we can find p. So p being kind of the relation to x bar. P is the sample proportion here. So let's say, so we're thinking about Minnesota, and we sample, we're going to take a sample, and N is 625 people. So we call up or get in contact with 625 likely voters. And we get the following information. 331 say Biden, and what is that, 294? 294 say Trump. Okay, now I'm making a couple kind of simplifying things right here. This is loosely based off of a poll from about a week ago, but I've made the assumption that everybody's answered, and there's only the two options, okay, or everybody's chosen one of the two options. So Kanye is not involved in this. Yeah, so we have this. So what do we know? We know P. We can find P as x divided by n, right? Where x is the number of successes or whichever value or whichever you deem as a success, right? So coin flip heads, same concept. So in this case, we can pick either one. It's not going to change our answer. So 331 divided by 625 tells us that Biden has about 52, I think it's 52.96. We'll say 0.53 just for sake of simplifying, and that's how you'd report it on the news. So 53%, and that is our best guess. Okay, so we took a sample, we found a P, that's our best guess for pi. Again, what we're using is this concept that, well, P is probably a pretty good guess for pi, just like we did over here. There. So we say 0.53. Again, that's the simple part. What's more difficult is how do we build in the confidence interval. So we're going to use a very similar system, and we'll just jump to the equation here. Is what we're going to build is P plus or minus Z. We can rely upon the Z distribution because we can just, in some sense, we don't have to know the population standard deviation because we can rely upon kind of building it from P, but also assuming kind of the largest standard deviation. So we can use the Z distribution, but then what we're going to multiply it, instead of sigma over square root of n, we're going to do square root of P 1 minus P divided by n. Okay, that looks a little cumbersome and weird, but if you recall back from our discussion around proportions, we calculated the following. We said the standard deviation was n pi 1 minus pi. Okay, so that's roughly, we're doing the same thing down here. So we're kind of incorporating sigma along the way. Okay, so that's where this falls out of. And so now all that's left to do is plug this in. So we have 0.53 plus or minus Z. Let's stick with our 95%. I think that's the most common in polling. 1.96 square root of 0.53 and then times 0.47, right? 1 minus 0.53. And then we took a sample of 625. So now we have everything. We just need to do a little math. You can double check my math. But I think we get plus or minus 0.0391. Okay, so or about 4%. We could do the exact same thing for Trump, but in this two case, we'd get the same. All these would be the same. It would just be 0.43 or 0.47 and 0.53. So the result would be the same. And so you could describe this as Biden 53% plus or minus 4%. What you more likely have seen it as, and how you would report this probably to the news, is you'd say, well, here's Biden. What did we say? 53%. Trump, 47%. And then down here, which oftentimes maybe a little smaller than I would prefer, or statisticians would prefer, you'd see this plus or minus 4%. Okay, and that's the way it would typically be reported. And this is that confidence interval. That's what they've done over here. Okay, and this is not much more simplified. In fact, the only difference in some of them that you'll see is maybe a third individual or some unanswered parts, but those are just small little tweaks. Basically, you can go become a pollster now. So, or at least you can back out kind of what they've done. So this is what you'd put up, plug into the news screen. Now, we've made some choices along the way. Okay, we decided to sample 625. What if we would have made a different choice? What if we would have said, let's sample 2,000? Okay, what if instead we would have sampled 2,000? How would our results change? Let's get rid of this. If we would have sampled 2,000, let's say, just for the sake of time here, let's say we also got 53%. Again, if you're doing a different sample, you might get 51%, you might get 54%. You probably wouldn't get right on 53. It might be 53.02, right? But let's say we sampled 2,000, and I guess what we would get is something like, just under or well, I guess we'd figure that out, 1,060 or something. Is that the right math? So Biden, 1,060. Trump, 940. And so we would go through the same process. We'd get 53 plus or minus 1.96, so z wouldn't change. We still want a 95% confidence interval. Square root of 0.53, 0.47, but we now have, what did I say, 2,000? And you can double check this math, but I think what we get is 0.53 plus or minus 0.0218 or something. Okay, so we have the same, again, assuming we got the same percentage, our confidence interval has shrunk. Took a larger sample, tighter window. Same thing that, well, I've erased it, but same concept here is as we get more information, the sample size goes up, we get more information, we have a better feel for where we think the value lies. So we would report that as, you know, I don't know what you'd say, 2.2% maybe. What if your boss came to you and said, that's all well and good, but we'd really like to see this as 1%. We want to be the leader, you know, ABC's running this poll. We want to get a nice tight window. We're gonna turn and talk about how do we choose the N? Okay, how many people do we need to sample? And it's not that hard of a calculation, and we'll see that here in a minute. Now, before we do that, I want to make note again that all of this is hinging upon good sampling. Just like our concern over whether we're sampling people walking out of the swimming pool, getting a biased result, that breaks down our best guess. Our best guess for the population height is no longer a good guess. Same thing is true here. We're assuming in these calculations that we're doing good sampling. And in fact, that's quite difficult for presidential polling or any type of polling. A few reasons for this. Number one, we're trying to find likely voters, right? We don't care what the general population thinks. We want to know for people that go into the polling booths or send in their ballots, what they're likely to do. So that makes it a little tricky. We don't know who's all going to vote. But it's also hard to get a good sample. So polling, 30, 40 years ago, typically what was done is they literally called people on their home landline. So that was a cord that used to go into your house, and that's how people had phones. Everybody had a phone, and a lot of people were home in the evening, and they would answer their phone. So we went through this tricky part about 10, 20 years ago where a lot of polls were still doing that. In fact, some still do. But when you do that, so let's just take a minute and think about this. If you call people on their landline in the evenings and think that's a good representation of the likely voters, what are you likely to end up with? Who's going to answer a landline in the evening? Just like if you sample right as diving practice is coming out, you're going to get more divers. If you call people's landlines, the only people that you know with a landline are probably your grandparents. Okay? So you're going to get a lot of older people. You're going to get people that maybe are home at the certain time of the day when you're calling. And you're going to get people that are going to answer a call from a stranger. And so it's no longer the case where a simple phone call does a good job of polling. Okay? There's some pretty complex ways to try to elicit good representative polling. And so if you go onto a site like 538 Politics, I think now they assign like a letter grade to each poll. So there are different kind of polling companies, ABC News, Rasmussen Polling. I don't know what they exactly are. I think ABC probably has maybe they're a B+. Okay, they give kind of a letter grade. I think Rasmussen is probably like a D- or something. Okay, so don't quote me on that, but they kind of give you a feel, try to give you a feel as to how well they think that they're doing in terms of trying to get the sample to match the population. So the same caveats are happening here. I just wanted to point that out. Now, let's quickly talk about your boss's goal here. She wants 1% on the bottom of the screen. So how many people do you need to sample? Well, we can do that, and we'll just jump straight to the equation. We can build that from the following equation. So n, what we're after, n, the number of people you need to sample. we're gonna incorporate a level of standard deviation. Okay, but we're going to, well, let me just write out the equation. We're going to incorporate our confidence interval, right? So the level, how many people you need to sample is going to change if you only want a 90% instead of a 95% confidence interval. And then we're going to have E, and E is that sampling error, that error that we're comfortable with. And then we're going to square that, okay? So let's put some real numbers to this. So in this case, before we sample, we don't know what the population standard deviation is. We don't know what values we're going to get. So thinking back here, what we're actually going to rely upon is 0.5, 1 minus 0.5, okay, because that's going to give us kind of the biggest standard deviation. That's the largest, thinking back to proportions here, that's the largest standard deviation we can have. 0.5 times 0.5 is the largest number anytime you go away from that. So 0.7 times 0.3 is going to be a smaller, that's just to highlight, 0.7 times 0.3 is what? 0.21. 0.5 times 0.5 is 0.25. So right in the middle there is the largest. That's why we're using it to give us kind of a buffer, or we're making sure that this is sufficient. Okay, Z, let's plug in 1.96. We said we want a 1%, so 0.01 for E. We square that. You can double check this, but what I get is 9604. Okay, and so you can go back to your boss and say, that's great, I can get you 1% on the bottom of the screen, but I need a bigger budget. I got to go contact 9,600 people. If you instead want a 4%, I only need to contact 625. Okay, so it gets pretty tough to get a smaller and smaller percentage here. And so that's why you tend to see, more often than not, you'll see a lot of 4%. You'll see some in the 2% range. You might see, what did we have? 2.2%. But you don't often see 1% confidence intervals in polling, because this is a lot more expensive than this version. And really, this is a better feel for it, but I think what they found is that when people look at these, when viewers do, they're not as impacted as maybe we should be, but they focus more on this stuff, and so they'd like to get out more sampling than kind of these tighter ones. So yeah, you will, they'll, when you look up, for instance, on 538, you can always, when you look at the polls, they'll tell you what the N is. So you'll see a lot of them around in this range of 600-700. You'll see some in the low thousands, but you won't see a lot that have contacted 10,000. So that we can find the N we need. This same process holds true for the more general kind of case here. So we can do a similar calculation. In fact, it's in the book, to find what size of sample do we need to be, within so many inches of our estimate, or sorry, to have a confidence interval that's only 1 inch wide instead of 1.57. We could have done a similar calculation. So yeah, so hopefully this gives you kind of a jump start as to how to get into Chapter 9, what we're trying to do. Again, a lot of it hinges on, we don't know certain things, how do we find them? And so hopefully this also gives you a way to interpret what's happening as you pull up polls in the next few days. So we'll leave it there. I'll stick on for a few minutes. Remember, I do have office hours later today as well.